Right now, your internet connection might actually be a ticking time bomb,
Oh, yeah. That's a good way to put it.
right? Just quietly counting down to a completely catastrophic failure in, well, exactly 2 weeks. And the fuse for this bomb, is an invisible scratch on a piece of glass that is roughly the width of a human hair.
It's crazy to think about because we talk so much about the cloud,
Right, the cloud.
or wireless signals just kind of floating through the air. And it becomes incredibly easy to forget the sheer physical vulnerability of the systems keeping us all online.
Yeah.
We imagine data as this weightless thing, but it is deeply, deeply grounded in dirt. It's strung up on wooden poles, and it is just constantly subjected to the elements.
And that harsh physical reality, that is the entire focus of our deep dive today.
Yeah.
We're looking at a hyper-focused technical bulletin. Specifically, it's tip number 5 from a source called the DAK Fiber Network.
Yeah, and to be clear, this isn't a press release or some consumer guide. It is a concentrated shot of industry advice, and it's aimed directly at the field technicians who literally build the global internet with their bare hands.
Exactly. And our mission today is to look at this one single tip sheet and understand how every single financial transaction, every streaming movie, every video call, it all relies entirely on these sub-millimeter physical connections.
Yeah, so the tip sheet focuses on a process called fusion splicing.
Fusion splicing.
Right. And for anyone outside the telecommunications trenches, fusion splicing is the act of permanently joining two completely separate fiber optic cables together.
Yeah.
And these cables, they're essentially incredibly thin strands of ultra-pure glass that are designed to carry light signals over these vast distances.
You know, when I was reading through the DAC source, the best way I could visualize this whole process was to think about plumbing.
Okay, plumbing.
Yeah, but plumbing built for light, rather than water.
Oh, I see what you mean.
Yeah.
Yeah. Like if you connect two PVC pipes under your kitchen sink, and you don't line them up perfectly flush, you get a physical leak. Water just slowly drips out and ruins your cabinet.
Right. Nobody wants that.
Exactly. But with fiber splicing, you are connecting two glass pipes. So if that connection isn't perfectly mathematically flawless, you don't leak water. You leak data. The light itself literally spills out of the joint and just disappears into the ground.
That analogy perfectly captures the stakes, I think, especially when you consider the scale of it all.
Yeah.
Because a water leak leaves a visible puddle, right? You can feel the dampness under the sink.
Yeah. You see the water damage.
Exactly. Yeah. But an optical leak in a fiber cable, it is completely invisible to the naked eye. The technician cannot simply look at the joined glass and see that data is spilling out. They can't see the light leaking.
Right.
They have to rely on testing equipment. And that brings us to the incredibly unforgiving standard that's established right at the top of the DAK document. The text states that a successful splice must have a loss of less than 0.1 dB. Okay, let's pause on that metric for a second.
Yeah.
Because just saying 0.1 dB, it doesn't quite capture the sheer absurdity of that requirement.
No, it really doesn't.
Because decibels, in this context anyway, they're used to measure the loss of the optical power as the light crosses that splice. But a decibel isn't a simple flat percentage. It's a logarithmic scale.
Yes. That logarithmic nature is key here, because a tiny fraction of a decibel represents this massive exponential shift in power. So demanding a loss of less than 0.1 dB is essentially demanding near-perfect light transmission across a physical, man-made break in the glass.
It dictates that almost 0 photons are allowed to escape that joint.
Exactly. 0. It is a level of geometric perfection that you would, expect to see in a sterile, climate-controlled laboratory.
But these technicians aren't in a sterile laboratory.
No, not at all.
They are out in the actual world. They're trying to achieve this sub-millimeter geometric perfection while standing in a muddy, freezing trench next to a highway.
Or swaying in a bucket truck 20 feet in the air.
Right, while it's raining. The contrast between the microscopic precision required and the chaotic physical environment of the job site, it's just staggering to think about.
It creates a massive amount of pressure on the person doing the work. And that pressure leads to the most fascinating and frankly terrifying warning in the entire DAK tip sheet. The document explicitly tells the technician, and I quote, "A bad splice will work today and fail in 2 weeks."
I have to admit, that specific timeline completely derailed my intuition when I first read it.
How so?
Well, if a physical connection is fundamentally bad, if the glass is misaligned or broken, why does it work today at all? The data is still flowing. The light plumbing isn't completely blocked, so why does it mysteriously just give up the ghost in exactly 2 weeks?
Right, seems counterintuitive. But the answer lies in how these tiny connections interact with the massive physical world around them. When a technician makes a bad splice, they rarely miss the connection entirely. They usually achieve a union that allows just enough light to squeak through, so it registers as a functioning connection on their testing meter at that exact moment in time.
So they see green lights on their end.
Exactly. They pack up their tools, the customer gets their Wi-Fi back, and everyone thinks the job is done. But that connection harbors an invisible flaw.
So we're talking about like a microscopic air gap, or maybe a structural weakness where the two pieces of glass just didn't melt together evenly.
Yes, a structural deformity. And because these cables are out in the elements, they are subjected to constant environmental stress. The Earth is constantly shifting. The glass expands during the heat of the afternoon sun, and then it violently contracts during the freezing night.
Oh, wow. I didn't even think about the temperature changes.
Oh, yeah. Or think about a heavy delivery truck driving down the street. It sends localized seismic vibrations straight into that buried cable.
So the environment is essentially waging this slow, relentless war on that tiny flaw.
That's a great way to put it. The stress compounds day after day. The thermal expansion and the physical vibrations pull and push at that compromised joint. And according to the hard-won industry wisdom encapsulated in this tip sheet, it takes roughly 2 weeks for that specific type of invisible weakness to finally succumb to fatigue.
2 weeks of just being slowly battered.
Exactly. The glass degrades, the microfracture widens, and the light finally stops crossing the bridge.
And because the glass is constantly shifting and degrading, I assume the light doesn't just stop instantly, right? The light slowly leaks out.
Right.
And for the person sitting in their living room, that invisible light leak translates immediately to the most universally hated phrase in tech, which the document lists as the very first symptom: slow internet.
Ah, yes. The dreaded buffering screen. It has the immediate localized fallout of a bad splice, but the DAK tip sheet traces a cascading domino effect of failure from there. So, following the slow internet, the next symptom they list is intermittent LOS blinking.
And LOS stands for loss of signal.
Correct. Loss of signal.
This intermittent failure is so much worse than a complete outage.
Oh, absolutely.
Because if my neighborhood loses power, or a backhoe rips a cable completely out of the ground, it's a hard outage. I'm annoyed, sure, but the provider knows exactly where the catastrophic cut happened. They dispatch a crew, I read a book, and I wait for it to come back online.
Yeah, it's cut and dry.
But an intermittent failure is psychological torture for the user.
It's agonizing because it creates false hope. The connection is hovering right on the bleeding edge of total failure. Like we said, the fractured glass inside the protective housing is shifting slightly. So imagine a strong gust of wind blows the aerial cable.
Okay.
It pulls the glass apart by a fraction of a millimeter and the signal drops.
Boom, you're offline.
Right. But then the wind dies down, the glass settles back into place, and the signal returns.
It's like a frayed phone charger cable.
Yes. Perfect example.
If you bend it at a very specific awkward angle, your phone starts charging. But the second you let go, where you bump the desk, it disconnects. That intermittent, flickering connection is infinitely more maddening than a cable that has just been cleanly sliced in half with scissors. You end up constantly hovering over it, waiting for it to drop again.
And that frustration, it extends well beyond the customer. It goes right to the technicians tasked with fixing it. The intermittent blinking makes troubleshooting incredibly difficult. The provider might ping the connection from their central office, and in that exact second, the wind isn't blowing, the glass is touching, and the system reports that everything is perfectly fine.
So they can't even see the problem.
Exactly. They are forced to chase ghosts in the network until the third domino falls.
And that's the final inevitable snap.
Yes.
The source lists it as a future break at splice point. The glass finally gives out completely. And that total failure necessitates the most painful symptom on the list, which is costly return visits.
Sending a field technician out in a truck is one of the highest expenses a telecommunications company can incur. The company has to pay the technician, who, by the way, might be the exact same person who made the compromised splice 2 weeks ago.
Oh man, the irony.
Right. They have to pay them to drive back out to the site, open up the subterranean vault or climb the pole, locate the tiny break, and do the entire job over again. It is a massive financial drain, all stemming from a single failure to achieve 0.1 dB perfection.
So, to prevent that agonizing chain reaction, the DAK tip sheet pivots from diagnosing the failure to outlining the strict physical mechanics of perfection. They provide this best practices checklist to ensure the splice survives past its 2-week expiration date.
Right.
And the very first instruction highlights just how delicate this medium is. It says clean fiber with alcohol wipe before cleaving, and cleaving being the industry term for cutting the glass.
Yes. And the order of operations here is non-negotiable.
It makes complete sense when you compare it to prepping a patient for surgery.
Okay, how so?
Well, a surgeon doesn't make an incision on a patient's abdomen and then pour sterilizing iodine over the open wound. You have to create a perfectly clean environment first before you alter the underlying material.
Oh, wow, yeah. That's a very vivid way to look at it, but it's spot on.
If a technician were to cut the fiber and then wipe it down with alcohol, the act of wiping could easily deposit a speck of dust or a piece of lint right onto the fresh, immaculate surface they just created.
And at the sub-millimeter scale of light transmission, a microscopic piece of lint might as well be a boulder blocking a tunnel.
A boulder.
Yeah, because the light hits the dust, it scatters into the surrounding plastic casing, and your decibel loss just skyrockets. The joint must be flawlessly clean before the actual cutting even begins.
Which brings us to the geometry of the cut itself. The document is absolutely rigid on this point. It states you must cleave at 90 degrees.
90 degrees.
There is no room for interpretation.
No. We have to picture what is physically happening inside the fusion splicing machine. The technician is taking 2 incredibly thin cylinders of glass, bringing them together face to face, and using an electrical arc to melt them into a single continuous strand.
Okay.
If both ends are cut perfectly at 90 degrees, they are completely flat. They mate seamlessly, surface to surface, with no gaps.
It's like pushing 2 perfectly flat Lego bricks together.
Yes.
They sit flush against one another.
Exactly. But if you have an 89-degree angle on one side and a 90-degree angle on the other, bringing them together creates a literal wedge of empty space. You introduce a tiny pocket of air.
And that air gap is the enemy of optical transmission.
It is the absolute enemy, because when the splicer arcs its electricity to melt those 2 ends together, the glass liquefies, right? But that trapped air pocket doesn't just disappear. It becomes a permanent bubble, or it becomes a structural deformity locked inside the newly formed joint. The light traveling down the fiber hits that deformity, refracts wildly, and spills out of the cable. The technician has just unknowingly built a ticking time bomb.
This structural vulnerability, it really explains the second half of that specific instruction in the text, where it says to check on splicer screen. Because the technician actually places these cleaned, cut glass strands into an automated fusion splicing machine. But they aren't looking at the glass itself to verify the angle.
They can't. Human biology is entirely inadequate for this task.
We just can't see it.
We do not have the visual acuity to look at a strand of glass that is thinner than a piece of thread and determine if the end is cut at exactly 90 degrees versus 89 degrees. The naked eye is just totally useless here.
It's fascinating. We've engineered an infrastructure that is so precise, our own senses are locked out of the building process. The technician has to surrender their judgment entirely to the digital screen. The machine uses its own integrated cameras to zoom in on those tiny glass faces, analyze the geometry, and basically tell the human, you have achieved geometric perfection. You may proceed to melt.
It is a profound reliance on advanced technology to build the very conduits that allow advanced technology to exist in the first place.
Okay, so you've prepped your surgical site, you've cleaned the glass, you've cut it perfectly flat at 90 degrees, the machine's optics give you the green light, and the electrical arc melts the 2 ends together perfectly. You now have a successful fusion splice with less than 0.1 dB of loss.
Success.
Right, the data is flowing. But the DAK document makes it clear that the job isn't over. This freshly melted joint is still incredibly vulnerable and requires a final, very delicate step to ensure it survives.
Yeah, the final mile of the installation process. The text mandates protect splice and sleeve and tray, no tension.
See, I found this instruction completely paradoxical.
Oh, really? Why?
Because the concept of protecting something physically, it usually implies securing it tightly, right? Tying it down or gripping it firmly so it doesn't move. But the text demands that the technician secure the splice in a sleeve and a tray while simultaneously ensuring it experiences absolutely zero physical tension. How do you physically hold something without applying any force to it?
I see what you mean. So the protection they are talking about is actually isolation.
Isolation.
Right. The sleeve isn't clamping down on the newly melted glass. The sleeve is a rigid tube that slides over the splice point and acts like an exoskeleton. Or, to continue your medical analogies from earlier, it's like a splint for a broken bone.
Ah, okay. So the sleeve creates a rigid physical barrier around the delicate joint so the glass inside can just float, completely isolated from whatever forces are pulling on the rest of the cable.
Precisely. The splint handles the blunt force, but that protective splint then has to be placed into a tray. And a tray is the small plastic housing where the excess loops of fiber are coiled up and stored inside a larger subterranean vault, or maybe an aerial enclosure. This is where the no-tension rule becomes incredibly critical.
Because if a tired technician is rushing to pack up the site, they might coil that glass a little too tightly into the tray just to make it look neat and orderly.
Yes, and the aesthetic desire for a neat tray is dangerous. If they pull the cable taut, they are applying pulling force, longitudinal tension, directly onto that freshly melted cellular level joint sitting inside the splint. The exoskeleton protects it from getting crushed from the outside, but it cannot protect the glass from being pulled apart from the inside.
Oh, wow. So the physical tension applied in that final, seemingly mundane moment of just packing up the plastic tray, that is often the exact mechanism that creates the invisible microfracture.
Very often, yes.
The technician finishes the job, closes the vault, and drives away, leaving behind a connection that is functionally working but structurally stressed. And 2 weeks later, the constant pulling force finally snaps the glass.
Exactly. Which brings us to the overarching philosophy of this entire technical bulletin. After laying out the severe consequences of failure and the rigid mechanics of success, the DAK Fiber Network concludes with a really profound psychological warning. It's contained in the final remember section.
Right. The text states simply, don't rush splicing. A clean cleave and proper alignment saves you a callback tomorrow.
This is a remarkable pivot, if you think about it. We have spent this entire deep dive analyzing the physical tension on the fiber optic cable, but this final warning directly addresses the mental tension on the technician.
You really have to consider the modern economic reality of the person doing this work. I mean, everything in our culture is driven by speed and volume. The technician likely has a dozen other tickets on their tablet that need to be closed today. The dispatcher is tracking their location. The customer is standing over their shoulder asking when the Wi-Fi will be back up.
The algorithmic pressure to work faster is immense. But this document is a quiet rebellion against that modern impulse. It demands a massive shift in mindset. You cannot rush physics. You cannot speed up the process of geometric perfection.
Don't rush splicing is almost a meditative instruction. It asks the technician to tune out the buzzing tablet, tune out the cold wind, and achieve a monk-like focus on a piece of glass they can barely even see.
Because speed is the enemy of a 90-degree angle.
Exactly.
Speed is what makes you forget to wipe the glass with alcohol. Speed is what makes you pull the fiber just a little too tight in the tray, creating the tension that leads to tomorrow's callback.
In this philosophical stance, it ties directly into the overarching mission statement of the DAK Fiber Network, which is printed at the very bottom of the source. Connecting fiber professionals, building better networks. They are drawing an unbroken line from the localized patience of a single technician working in a muddy trench, all the way up to the macro-level reliability of the global internet.
You fundamentally cannot build a better network globally if you are rushing the microscopic connections locally. The integrity of the massive whole relies completely on the integrity of the smallest invisible part.
It is a sobering reminder of just how fragile our sprawling digital systems really are.
Yeah, it really is.
We've covered a tremendous amount of ground today from one incredibly dense technical tip sheet. We started by looking at a terrifyingly small margin of error, demanding less than 0.1 decibels of optical power loss. We explored how failing to meet that standard, even by a tiny fraction, creates a maddening domino effect. The invisible light leaks out, the end user suffers from slow internet and agonizing intermittent signal drops, the glass eventually breaks under environmental stress, and the telecommunications company has to fund a massively expensive return visit.
And to avoid that nightmare scenario, we unpacked the meticulous surgical process required to achieve absolute perfection in the field. Crucial order of operations of cleaning the glass before cutting it. The necessity of a flawless 90-degree cut to avoid trapping those air bubbles. Surrendering to the digital optics of the splicing machine, and, of course, the paradox of securing the final joint in a protective tray without applying a single ounce of physical tension.
It is a high-wire act of precision engineering performed in the dirt, and it all boils down to that final philosophical plea for patience. You cannot rush the physical foundation of the modern world.
Every time a surgeon completes a remote robotic surgery, or a family streams a movie in 4K, or a financial institution transfers millions of dollars across an ocean, they are relying entirely on the meditative patience a field technician had on a random Tuesday, months or maybe years ago.
And that reliance brings me back to the thought I want to leave everyone with today. A concept to just mull over the next time you connect to a vital video call, or confidently send a massive file across the world in an instant. The DAK source explicitly states a chilling physical truth. A bad splice will work today and fail in 2 weeks.
The invisible time bomb.
The time bomb. Which implies a truly terrifying reality about the massive infrastructure that runs every aspect of our lives. Right now, at this exact second, all over the world, buried under the sidewalks we walk on and hanging from the poles above our cars, there are countless hidden flaws. Millions of sub-millimeter glass connections that are transmitting our data perfectly in this exact moment, but they're fundamentally compromised. They were rushed by a tired technician. They were cut at 89 degrees. They were pulled with just a tiny bit too much tension in the tray.
They are silently degrading, widening by a fraction of a millimeter every single time a heavy truck drives by.
How much of our daily high-speed connectivity is currently running on borrowed time, quietly ticking down to that 2-week expiration date without us ever knowing? The next time you see a router light flicker and die, you have to wonder, was that just a random glitch? Or was it the physics of the universe finally catching up to a microscopic mistake made exactly 2 weeks ago?